So now that you've seen the structure and functionality of the program, now that we've talked about how to visualize what's going on, let's finally get down to the fun part, which is looking at code. And hopefully the code will be a lot easier to understand now that we've sort of looked at it from a couple of different points of view. So we're going to focus on the process stream method, which is a hook method that's defined in this ImageStream parallel.java file. And it's kind of the workhorse method in the entire thing. It should look very familiar at this point. The first thing we do is we make a call to this getInput helper method. That actually comes from the underlying StreamGang framework. And we hook it up so it gets input from wherever the input comes from. The input could come from users typing into a dialog box in an Android GUI. They could read it from a file. We could pre-code this stuff to come from a hard-coded list for testing purposes. We could read it from a file, whatever you want. You get the images, you get the URLs from the getInput method. We then convert the URLs into a parallel stream. So we convert the list of URLs into a stream of URLs, which was a parallel stream of URLs. And then we go ahead and we're going to filter such that only non-cached images will be allowed to continue flowing through the stream. And that uses our good friend, the filter method. We've seen filter a million times before. And remember that filter can return less than or equal to the number of input elements as the output of the stream. If nothing has been cached, it'll be equal to the input. The output will be equal to the input. If something is cached, then we'll have fewer elements coming out. If everything's been cached, we'll get nothing out. So it'll just be a no op at that point. Yes? Not is defined as a predicate I wrote myself. Now, there's a couple of different ways to do this. One way you could do this would be to use a lambda expression that checks to see whether URL cache returns true or false. You could do that way. Another thing you could do is you could cast URL cache to a predicate and then use the .negate method on it. And then the way I do it here is just to use not because it was shorter. And so, but not pretty much just, it's a predicate that takes the input and then negates it. So true becomes false, false becomes true. But yeah, that's a great question. So here's what URL cache could look like. There's lots and lots of different ways to do this. So this particular program will take the URL and then go and check to see whether we've already got a file with this name in our file system. And it ends up calling this helper method, which checks to see if a file with this name already exists. And the name is encoded in such a way that you would know if you already had seen it before. So we check to see if the image name already exists. And if it does, we assume it's been cached. There are obviously better ways to do image caches. The right way to do it is probably to implement something along the lines of what a web browser does, where you've got like an age header, and you have like this max age, and you use that, and then after a certain amount of time, you consider the image to be stale, and you have to go and re-download it again. We could certainly have done that, but I would just make it easy. And the cool part about this, of course, is if you want to make a better cache, all you do is just, implement a better cache, and everything else stays the same, right? So you get the basic structure, which could remain identical even if piece parts improve. The next thing we're going to do is we're going to call map. And remember, map takes an input stream, does something to it, and then produces an output stream, which might change the type. In this case, it does, because it goes from a stream of URLs to a stream of images. And the number of elements in the output stream must match the number of input stream elements unless an exception is thrown, which let's assume it's not. So here's what blocking download looks like. So blocking download, as the name suggests, it can block. And so it's going to download all the content from a URL and convert it into an image. So there's a method, a helper method called downloadImage, which takes a URL and it returns an image. Image is my data structure that keeps track of image-related data. And under the hood, it uses something called blocking task call in manage blocker. And we're going to talk more about this soon, probably maybe even starting Wednesday, when we start talking about the fork join pool. And there's a really cool feature there, which I've mentioned briefly before, called the manage blocker interface. And blocking task call in manage blocker is a little wrapper around the manage blocker interface that makes it convenient and easy to use things using Java 8 supplier semantics. And so the long and the short of it here is that this ability to download things in the common fork join pool is going to make it possible to increase the number of threads in the common fork join pool when blocking downloads occur. And why would we want to do that? We want to do that because, as we talked about earlier, and we will go into more detail here soon, with blocking I/O, while I/O is blocking, you want to be able to switch contexts and let another thread run while other threads are blocked. And if you don't have extra threads, then you'll end up underutilizing performance. And so we'll talk more about this formula, but there's basically a formula which is used for I/O-bound tasks on an n-core CPU, where you take n, where n is the number of cores, and you multiply it by 1 plus wait time divided by service time. And I'll talk about this in more detail later, but in a nutshell, if wait time is high relative to service time, like if you're blocking, where wait time would be higher, then you're going to end up with more threads. If wait time is very low, like in compute-bound operations, then you're going to end up with basically n threads. So it's just a little formula. We'll talk more about it. You can read more about it at this link down here, and I'll go through it in detail when we get there. But that's what we're doing here to make sure that the pool has enough threads to be able to run in parallel. So we end up, when all is said and done here, we end up with a stream of images to non-cached URLs. And then we're going to go ahead and apply filters. And we'll end up with more elements coming out of this at the end. And that's because flat map, as we talked about before, can have more elements or less elements or equal elements or whatnot than the number of elements it was given. In this case, it's going to be more because each image has multiple filters applied to it. Here's apply filters. In a nutshell, apply filters is going to take all the filters, and in parallel, it will apply them to the image. So for each image, all the filters will be applied, and we'll end up with a stream of transformed images coming out of apply filters. So that's why we're going to have more elements coming out of here than we put into them. And then the final thing, obviously, is collect, which reduces all the elements into a single result, which in this case is a list, or an array list, of filtered and stored images. That's what we get when all is said and done. And of course, collect also triggers all the intermediate operations, turns them into a list, and then we go ahead and print how many images we transformed. Once they're stored, then another piece of the program will actually display them. This is just here to kind of give you some logging information that you could use to satisfy yourself that the program is working properly. Okay, so that's the end of the code walkthrough. I think you'll agree that this looks very much like the other programs, which is good. That's the whole point of streams, is to have a very canonical look and feel to your code. And hopefully you'll also appreciate the fact that the logic in those steps and those operations in the stream match very closely to the domain intent of the program we're implementing.